Welcome to Qt e-Learning channel. In this lecture, we will discuss the Erosion-Corrosion. Description of damage. Erosion is the accelerated mechanical removal of surface material as a result of relative movement between, or impact from solids, liquids, vapor, or any combination thereof. Pure erosion, sometimes referred to as abrasive wear. Erosion-corrosion is a description for the damage that occurs when corrosion contributes to erosion by removing protective films or scales, or by exposing the metal surface to further corrosion under the combined action of erosion and corrosion. Affected materials. All metals, but mostly carbon steel and copper alloys in refining. Refractories are also affected. Most commonly affected are materials without true passivity, where the corrosion rate is limited by a protective corrosion layer or inhibitive film. Critical factors. With solid particle mechanical erosion, metal loss rates will depend on the velocity and number of impacting particles, as well as the size, shape, hardness, and density of the impacting particles, the hardness of the material subject to erosion, and the angle of impact. Softer alloys such as copper and aluminum alloys that are easily worn from mechanical damage may be subject to severe metal loss under high-velocity conditions. Increasing the hardness of the eroding metal component can reduce the rate of erosion damage. However, this may not be effective where corrosion plays a significant role. For solids entrained in a liquid medium that also has a corrosion component, the same factors apply as with solid particle mechanical erosion described in previous slide. However, with the solid particles removing any protective scales or other protective barrier on the metal surface, the rate of metal loss can be much greater than what is normally seen from the corrosion mechanism alone. For corrosive liquid droplets entrained in a vapor, metal loss rates will depend on the velocity and number or rate of impacting droplets and the corrosivity of the liquid. Many corrosive liquid environments will exhibit velocity-accelerated corrosion. In some cases, there is a threshold velocity below which corrosion is minimal but above which corrosion becomes significant. In other cases, there is no specific threshold. The highest corrosion rates simply occur where the velocity is greatest. Table shows erosion-corrosion rates for a number of metals in seawater at different flow velocities. As the table illustrates, some alloys, particularly copper alloys, have an apparent threshold velocity above which the rate of metal loss increases significantly. Affected units or equipment. Erosion can be caused by gas-borne catalyst particles or by particles carried by a liquid such as a slurry. In refineries, This form of damage occurs as a result of catalyst movement in FCC reactor regenerator systems in catalyst handling equipment, valves, cyclones, piping, reactors, and slurry piping coke handling equipment in both delayed and fluidized bed cokers and as wear on pumps, compressors and other rotating equipment. Crude and vacuum unit piping and vessels exposed to naphthenic acids in some crude oils may suffer severe erosion-corrosion metal loss depending on the temperature, velocity, sulfur content, and the total acid number level. Example of erosion-corrosion as shown in figures. Appearance or morphology of damage. Erosion and erosion-corrosion are characterized by a localized loss in thickness in the form of pits, grooves, gullies, waves, rounded holes and valleys. These losses often exhibit a directional pattern. In liquid lines containing particulate, low velocities less than 1.5 meter per second can allow solids to tumble to the bottom and cause erosion or erosion-corrosion in the 6 o'clock position. Failures can occur in a relatively short time. Prevention mitigation. Improvements in design involve changes in shape, geometry, and material selection. Some examples are increasing the pipe diameter to decrease velocity, streamlining bends to reduce impingement, increasing the wall thickness, and using replaceable impingement baffles. Improved resistance to erosion is usually achieved through increasing substrate hardness using harder alloys, hard facing or surface hardening treatments. Erosion-resistant refractories in cyclones and slide valves have been very successful. Erosion-corrosion is best mitigated by using more corrosion-resistant alloys and/or altering the process environment to reduce corrosivity. Higher molybdenum-containing alloys are used for improved resistance to naphthenic acid corrosion. Heat exchangers utilize impingement plates and occasionally tube ferrules to minimize erosion problems. Inspection and monitoring. Manual UT grids or automated scans can be used to determine the extent of erosion at susceptible areas, such as changes in direction, changes in diameter, or other turbulent areas. Profile RT can be used to detect areas of erosion but may not be able to determine the actual remaining wall thickness. UT thickness is normally used as a follow-up technique to quantify wall loss. Guided wave testing can be used as a screening technique in certain applications where changes in piping direction will not impede the effectiveness of the examination. Permanently mounted thickness monitoring sensors can be used. Infrared thermography scans can be used on stream to detect refractory degradation, potentially due to erosion. Specialized coupons can be used to determine if erosion is a potential concern. Related mechanisms to erosion. Erosion-corrosion is cavitation. The summary of erosion, erosion-corrosion. Description: erosion-corrosion occurs when corrosion contributes to erosion by removing protective films or scales, or by exposing the metal surface to further corrosion. Erosion and erosion-corrosion are characterized by a localized loss in thickness in the form of pits, grooves, gullies, waves, rounded holes and valleys. These losses often exhibit a directional pattern. Temperature range. Service temperature. Affected metallurgy. All metals, but mostly carbon steel and copper alloys in refining and refractories. Prevention. Changes in shape, geometry, and materials. Improved resistance to mechanical erosion. Using more corrosion-resistant alloys and/or altering the process environment. Inspection methods. Manual UT grids or automated scans, profile RT, guided wave testing, saturated low-frequency eddy current and infrared thermography. Practice time. Question number 1. By removing surface protective film, corrosion contribute to Answer is A. Question number 2. Erosion and erosion-corrosion mechanism are characteristic by Answer is C. Question number 3. Erosion-corrosion is best mitigated by Answer is D. Question number 4. Visual examination of suspected erosion-corrosion areas is only one means of inspection, others include Answer is D. This lecture is prepared by Samir Saad and this is his profile. Thanks a lot for watching and please waiting us for the next lecture.